Okay, consider the following annotated program called n power m, which allegedly computes n to the power of m. The first thing we have to do is compute a table by filling in the values of r and I after we run the loop at least 4 times. So we're told what the values of I and r are before the code runs. We don't have enough information to deduce what m and n are, so I'm just going to let them be arbitrary. So let's pretend m is some number bigger than 0, and n is some positive constant. So in the first loop, what happens? R is replaced with r times n, so 1 times n is n, and I is incremented by 1, so 0 plus 1 is 1. In the second loop, we do that again, so multiply r by n ends at n squared, I goes up, n squared times n is n cubed, n goes up, and then n cubed times n is n to the 4, and n goes up. And it's a lot more obvious spotting the invariant when you leave n as an arbitrary n rather than picking n equals 2 or n equals 3, because now it's super obvious what the invariant is, right? Clearly, at all points in the loop, r is going to be equal to n to the power of I. So for the second part, identify an invariant. I'm going to use the word I instead of p, because I've reserved p for the precondition. I'm going to guess that this here is my invariant. So it needs to be strong enough and weak enough to imply and be implied by these statements. So let's check this one first. R equals n to the power of I, and it's false to say the loop condition is true, so that is I is greater than or equal to m, implies R equals n to the power of m. Well, it doesn't look like this is going to be true, right? This is not sufficient information to conclude what I want. That means my invariant, while it is an invariant, it's too weak. So to rectify this, what I do is I basically have to work out what's the minimum extra piece of information that needs to be added here that is still invariant, still always holds as the loop runs, such that I can conclude R equals n to the power of m from just the invariant and the loop condition being false. Well, I kind of want I to be equal to m, because then I can just replace the I with m, and then I get what I want, right? So how am I going to achieve that? Well, the loop condition being false gives me I is greater than or equal to m. So what's the minimum extra piece of information I can add? Probably I is less than or equal to m. Now I need to check that this property here, my new invariant, is, well, you know, invariant. So is it the case that as the loop runs, I is always less than or equal to m? Well, if that's not the case, then we don't ever enter the loop, right? Because the loop keeps running while I is strictly less than m. So it looks like that is indeed a property that is invariant, and so I can add that to my invariant here. So it's now strong enough to imply the post condition because I kind of reverse engineered it so that it was. It also needs to be weak enough such that it's implied by the precondition. So what we can do is we can jump that onto a new page. And I need to also check that it is indeed weak enough. So I need that if m is greater than or equal to 0, and if n is positive, and if r is 1, and if I is 0, does it imply my invariant? R equals n to the I, and I less than or equal to m. Okay, well, if r is 1, and I is 0, and n is positive, any positive number to the 0 is 1, so this part checks out. And if I is 0 and m is non-negative, then certainly I is greater than or equal to m, so that part checks out too. So yes, it does indeed look like it's weak enough. And we're pretty sure it's an invariant just by sort of eyeballing the table. It looks like this property will always be true. So for this question, state the invariant, no formal proof. Okay, there's my invariant. Part 3, identify a variant E for the loop. Using the same invariant I as in the previous exercise, these are the following two properties. So it must be greater than or equal to 0 when the loop is entered. So that is, we need that invariant I, and loop condition B implies the variant is positive. So expanding that out, I need R equals n to the I. and I is less than or equal to m, and I is strictly less than m, implies the variant is greater than or equal to 0, and it's, well, got to be variant. So every time the loop body runs, it decreases by at least 1. So if I look at the code that I'm given, I'm looking for something that's always counting down. And it looks like I is counting up towards m. So as a good guess, we could try just m minus I as my variant. Well, it is indeed a variant, because every time the loop runs, I gets 1 bigger, so m take I gets 1 smaller. And it satisfies the property here that we want, because these 3 properties here imply that the variant is non-negative, because if we just take this property and rearrange it, we get m take I is greater than or equal to 0, which is precisely what we want. So, what's the question say? Identify a variant. Okay, cool. Here's my variant. Give a whole logic proof of the following total correctness while loop only. So I've got my invariant I, I've got my variant E. This is the statement that I now have to prove. So how am I going to do that? If we jump to the while loop total correctness on the rules sheet, I actually really have 2 statements I need to prove. I need to prove I and B implies the variant is greater than or equal to 0, which we just demonstrated before on paper. So we know that part's true. M take I is positive, so that was easy by math. And the tricky part is we have to prove this whole statement here. So I have to prove the invariant I and the loop condition B and the variant is equal to some variable that doesn't show up anywhere else, so we'll use A. And then you have the code, which is these 2 statements. And then we have, as a post condition, the invariant I again. And the variant has gotten smaller. So m take I is now strictly less than A. So this is the statement we are required to prove. Okay, so how are we going to do that? Well, this to me looks like a sort of sequencing problem, right? So we'll copy up the bottom 2 statements like we usually do and do assignment rule backwards. So we take all the i's in here and replace with I plus 1s, being very careful to add brackets where necessary so as to not sort of screw up the meaning. So here would be a classic trick. If you just did that, that would be wrong, right? Because it's m minus I, and we're replacing I with I plus 1. So now it's m minus I plus 1. So if you don't put the brackets here, you mess everything up. So this precondition becomes my new post condition. I have the second piece of code, and I have the original post condition. So if I can prove these 2 statements, then I can prove this statement via sequencing. Second statement we just did by our assignment. The first one is not so obvious. We're going to have to do assignment rule backwards and then do some precondition juggling. So we'll copy up this, and then we'll replace all the r's with r times n's. And obviously doing this on a computer is a lot easier than writing it up by hand, so I recommend you do that for the exam. That's all the r's there are, so that's it. And then hopefully this statement here is a stronger statement than this statement here. Is that necessarily true? I don't know. We better check it out. So what do I want? I want to show that if r equals n to the I, and if I is less than or equal to m, and if I is strictly less than m, and m take I equals A, then I can conclude r times n equals n to the power of I plus 1, and I plus 1 is strictly less, I plus 1 is less than or equal to m, and m take I plus 1 in brackets is strictly less than A. Okay, well if we take this statement and multiply both sides by n, we get this statement here, so that checks out. And if I is strictly less than m, then that means it's got to be at least one smaller, which means if you add 1 to it, it's either equal to m or still less than m, so that implies that, and that checks out. And if m take I is equal to a, then surely if you minus 1 away, it's now less than a, which is the same thing as minusing off I plus 1 in brackets. So that implies that statement, and we're all good. Cool. So we know this is now true by math. And now I better had put in some line numbers here so we can keep track of what's going on here. That's line 2, line 3, line 4, line 5. Okay. So this was an assignment. This was math. This was precondition strengthening by lines 1 and 2. This was assignment. Line 5 is gluing lines 3 and 4 together with the sequencing rule. At which point, this is now in the right form for me to use my total correctness rule, right? So 6 is true by logic, or by math or whatever. And so now I can glue these two statements together and apply the total correctness rule. So we're going to get the invariant I, while b do s, I'm just going to write loop for all of this stuff, invariant and not b. And that's my b here. So, which that just matches using the while rule, which is precisely the statement we were looking to prove. Note that this isn't actually the same as the original statement. The questions asked us not to quite go that far, but we certainly can. While we're here, we may as well finish off the proof. So we can go further and actually prove this original statement. And how are we going to do that? So basically what I have to do is I have to do precondition strengthening and postcondition weakening as appropriate. So if we were to continue, I would require that this statement here is a stronger statement than the one I've got. So m is greater than or equal to 0. And n is positive, and r is 1, and I is 0 implies the precondition here that I've got. We know that's true because we sort of checked that earlier when I was checking if the invariant was valid. That's true by math. And I forgot to put a rule here. That's while total correctness, line 6. Okay, so because this is true, I can strengthen my precondition, do a switcheroo. So that's true by precondition strengthening, lines 7 and 8. And then we also have that this stuff here implies the postcondition that I desired, r equals n to the power of m. And why do I know that to be true? Because I sort of rigged my invariant such that the statement was true back when I was picking the invariant earlier. So I know that's also true by math. And then I can take this statement and weaken the postcondition like so. So postcondition weakening, lines 9 and 10. And this now precisely matches the statement that I desired. So the exam question didn't actually ask me to do that, and only asked me to go this far, but maybe they ask you to prove the entire statement, which is what I have done here. So, there we go.